In this video, I'll talk about the electric field due to a charged ring. So let us consider we have a charged ring. So this is a charged ring here. This is uniformly charged. And we are interested in finding out the electric field at a point P, or at a distance at this point P, which is at a distance R from this charged ring. All right, so we call this is an origin, and we assume this is x-axis, and let's call this is an y-axis. This is the y-axis. Okay, and this ring is uniformly charged, and we have to find out the total electric field at this point P. How are we going to do that? So what you're going to do, we'll just take an elementary charge at this point right here. Let me erase this one, I think. Okay, so we're going to take an elementary charge at the right here at this point. We call that elementary charge dq. Okay, the total charge, the total q is the total charge. Q is the total charge. That means the total charge, this Q is uniformly distributed over the entire ring, and we're just taking in a tiny segment which charges dq. All right, and let's consider the radius of the ring is a. So a is equal to radius, and this distance, the distance from this point, let's say this is x. Instead of r, we assume this is x because it is along the x-axis. Okay, oops, so this is x. Now, in order to solve this problem, we have to first find out what is the electric field at this point due to a tiny charge here, and at the same time we also take the tiny charge onto the other side of the ring, which is again the dq. All right, so the electric field at this point P due to this charge d is away from the charge. Okay, it is away from the direction, is in this direction. This is the direction, and I'm calling simply, oops, I'm calling this one as a dE, and the dE is because it is only coming from the elementary charge d, this dq. The same way we also going to find out the electric field at this point P due to this tiny charge. The tiny charge, due to this tiny charge, the electric field will be again in this direction. So let's call this is a dE one more time, and we assume this angle is theta, and this angle will also be theta due to the symmetry. Okay, this distance is x, this distance is x, this is a, so this distance will be r will be equal to, by Pythagoras theorem, will be equal to a square plus x square. Now the next thing we're going to do is we're going to resolve this electric field into two components. Okay, as this angle is theta, this angle will be theta, and this angle will also be theta. So now let's focus on to this one first, this part here. So the component of this electric field along the x-axis will be dE. Let me erase this one here for now. It will be dE cosine theta, and along the y-axis it will be equal to dE sine theta. The same way now we're going to resolve this electric field along the two axes or two components. Along the x component it will be dE cosine theta, and along the y component it will be dE sine theta. Okay, so what you see now, the dE sine theta, this dE sine theta and dE sine theta are equal and opposite directions, so they cancels out. So we do not have any electric field along the y direction because they are equal and opposite, and along the x-axis they add up together. Okay, so the total electric field, the electric field due to these two charges at this point, the total electric field at this point due to these two tiny charges is only along the x-axis, only along the x-axis. So what is the total electric field then? The total electric field due to these two charges, the tiny charges which is along the x-axis, can be given by let me write down this way. Okay, the total electric field which has only the x component, because as you see the y component cancels out, so it has only the x component. The y component cancels out, so it has only the x component, which is given by the dEx. So we now have to integrate the electric field over the entire region, because we have found what is the electric field due to this point charges, and now we're integrating over the entire region. This integration now gives for the entire region. That's how we find the total electric field. And the this x means the total electric field is only along the x-axis. Okay, and here I'm just writing down over the entire ring. The integration is over the entire ring. Okay, the field is only along the x-axis. X-axis. So now let's simplify this one now, and we can see from this diagram the total electric field along the x component due to this tiny segment is dE cosine theta. So here I'm doing ring, and then this field is dE cosine theta. Okay, then because dEx due to the top part is dE cosine theta. All right. Okay, now what is the charge here? The total charge here is dQ, and how do you find out the electric field at this point? So the dE and dE is given by K dQ over R square, and R squared is equal to let me write down here a note. Remember, how do you find out the electric field? The electric field is given by K, the charge over R square. Okay, and here I'm using the dE because we're just taking a tiny segment of charge. So in this case, this tiny charge is dq, so just writing down the dq, and r is this distance here, the distance, this distance, and this distance is equal to a square plus x square square root, and it's a square here, so I can simply write down a square plus x square and then a square root a square, which can be again simplified as simply equal to a square plus x square. And also the cosine theta from above, just look at this triangle here, this triangle. What is the cosine theta? In this case, the cosine theta is equal to b, which is equal to x over r. So the cosine theta is equal to x over r. And what is x? X is a constant, and r is equal to a square plus x square. And this is also a constant. R is a constant, it's not changing. It doesn't matter which where you choose, r is always a constant here from all location. So r is constant, it is not changing. So now let me write down cosine theta value, which is x over a square plus x square. Okay, so now let's take all the constant out. K is a constant, x is constant, the x is the distance from this point to this point, so this is a constant, and this is also a constant. So if I take out all the constant, what I get is k times x times divided by, and this is x square, so a square root and a square will cancel out, and then you have a square root here. So if I add them together, what I get is x square plus a square 3 over 2, and then this is the dq over the entire ring. Okay, so what does this mean? This means if I add up all the charges, all the elementary charges at all locations, dq, then that gives me the total charges onto the ring. So this one will be equal to k x, and this value is now equal to, this is now the total charge, this is now equal to the total charge onto the ring. So this is equal to q over x squared plus a squared over 3/2. And this is the electric field due to a charged ring at any locations. Okay, on x-axis. This is on x-axis. Okay, that means along this line here, along this line here. Okay, let me now talk about a special case here. A special case. First special case I'm going to talk about is x is equal to 0. What does that mean? That means if this point x is equal to 0, that means if this point is right here at the center, and the point P is here at the center, then you see this is due to the symmetry. The total electric field, the electric field at this point due to this charge will be in this direction, and due to this charge it will be in this direction, due to this charge it will be in. So the total electric field will cancel us out, and we can also plug into this equation. If x is equal to 0, what you get is the total electric field is 0. So what you have is Ex is equal to 0. The total electric field is 0. And this makes sense because if you have a charge here, then the electric field will be directed at all points in radially outward directions. So the total electric field will be 0. Now let's talk about the second special case, which is now x is much greater than a. What does again this means? That means if this point P lies at a very far away, if this lies very far away, then to this point P, this just looks like the entire ring looks like a point charge. So you will see something as a point charge. If this point is P is very away, then to this point P, the entire ring looks like a point charge. And mathematically, how can we write down this equation? If x is greater than a, then that means x squared plus a squared can be approximated simply as an x squared. Okay, the a will be negligible. If you have 1 lakh and if you add just 1, or let's say 1 million plus 1, it will still get 1 million. You can ignore a 1. That's how small a will be. So now we can write down this equation now. This equation. So how can you write down the equation then? The Ex would be simply equal to Kx cube, then x squared plus a squared will be simply equal to a squared. So a squared, then you have, x squared, then 3 over 2. This is equal to k q over x squared. This is exactly what I mentioned earlier. What does this equation tell you now? This equation tells you that if the point P is very far away, then the entire ring behaves as a point charge. This formula is for a point charge, kq over x squared. So it just behaves like the entire charge. This entire charge is centered at the origin, or at this point P, or this point O. Okay, so if this point P is very far, the entire charge appears to be concentrated at the center of the ring. So this is it for the electric field due to a charged ring. If you have any questions, any comments, please